Welcome back everyone, Patrick here, moving on to another question dealing with quadratics. This is a word problem here. Now before getting into it, just want to mention that this over here, you don't have to write out. It's on the lecture notes that you could print out. It's on the website, and if you're watching this on YouTube, you can go to the website. There's a link in the description box, and I highly recommend printing the lecture notes out so you don't have to write all this out, and then you can follow along in order because there's a lot of carryover from previous videos. There's a certain order that I'm making these videos in. So let's see what we're dealing with here. We're told that a square grass field has a side length of 20 meters. A square pool with a side length of X meters is to be placed in the center of the grass field. And then we have these three questions. So part A, we have to find an equation representing the area of the grass after the pool is installed. Part B, we have to graph the relation from part A and adjust your values for, or adjust your graph rather, for the valid values of X. And then in part C, we have to explain how does the equation and graph change with changes in the area of the field. So notice that in this case, the field has a length of 20 meters, but how is that going to change part A and part B if that 20 meters either goes up or down? So let's erase this here, and what I'm going to do is I'm actually going to start off with a diagram just so we visually see what is going on here, what we're working with. So we have a square grass field, so let's first draw that. So we got this, we got a grass field, and then we're told the side length is 20 meters. So we got 20 meters here, we have 20 meters over here. And then we're told a square pool is going to be placed in the middle. Okay, so let's draw a square pool like that. And we're told that the square pool has a side length of X meters. So we don't know what the side length is, so we're going to put a variable X there. So this here is going to be the pool, and it's right in the center of this grass field. Right, so that's what we're working with in this case. Now, in part A, what they're asking for is an expression for the area of the grass that's remaining, right, which is going to be this part over here, the non-shaded part, pretty much, after the pool is installed. So how can we get the area of the non-shaded part? Well, an intuitive way to go about it is we can get the total area over here, the total area of this square, and then subtract the area of the smaller square. And that's going to give us that remaining area, which is what they're asking for in part A, the area of the remaining grass. And so the area of the remaining grass, let's call it capital A, that would be the variable we're going to use. It's going to be the large area, which is going to be 20 times 20, or 20 squared, minus the small area, which is going to be X squared. Right? The area of a square is just the side length times the side length, right? Or the side length squared. So we took the large area, subtracted the small area. And then if we make this look a little nicer, what is 20 to the power 2? Well, that's just 400. And then we have just minus X squared, like that. Right? So notice that we end up with a quadratic relation here. Right, for the area, remember this A here represents, let's maybe actually write this down. So the area represents the area, or the A represents the area of the remaining grass. It's a good habit to just write out the descriptions of these variables. And then X, we're given in the question what X represents, but let's just say it's the side length of the pool. Right, so notice for the area of the remaining grass, we actually end up with a quadratic relation over here. So if the pool, let's say it has a side length of 5, then the pool would have an area of 25, right, 5 to the power 2. So then the area of the remaining grass would be 400 minus 25, which would give us 375. Right? And so that's going to change. This area is going to change in relation to whatever that x value, whatever that side length of the pool is going to be. Now, what we have to do in part B is we actually have to graph this over here. So notice what we can do. We draw out a Cartesian plane. Notice that over here we're going to have the x value, and then notice that the y-axis in this case is actually the area axis. Right? It's not a y, it's an a in this case because we're dealing with a word problem. Now, how is this graph going to look over here? Well, notice that we can actually use transformations to figure out how this looks. So if we start off with y equals x squared, what we're transforming this to is y equals, if we make this look a little nicer, I'm going to bring the negative x squared in front, and then we'll have plus 400. Right? Negative x squared plus 400, 400 minus x squared, those are the exact same thing. So let's forget about the word problem for now, and let's just deal with these abstract quadratics over here. So if we start with x squared, which is just that base function, that looks like that, what are the transformations that we undergo over here? Notice that the a value is -1, and then there's a k value of 400. So what we're doing is we're actually flipping this, right? It gets reflected in the x-axis. That's what the -1 represents. And then it gets shifted up by 400, a k value of positive 400. And so we shift this upside down parabola up here. And so it's going to end up being a parabola that looks like that. And what's this vertex here going to be? Well, the vertex, notice that the vertex here is just 0 and 0. Well, if we shift it up, the x value is still going to stay the same. And now the y value is going to be 400. All right. And so this shifts it up, the 400, and then the -1, it just reflects it. Means it flips the parabola. There's no other vertical stretch or compression. There's no h value, so it's not moving left or right. We just end up with this graph over here. Okay, so if we take this and graph it here, I'm going to adjust the graph in a sec, but let's just graph it as an abstract quadratic for now. So this here is at 0 and 400. Okay, and that makes sense. Notice if we plug in 0 for x, what's the a value going to be? Well, it's going to be 400. So that's actually the maximum point. That's the maximum area of the remaining grass. If you think about it, the maximum area of the remaining grass is if we don't have a pool, right? If that x value is 0, which would be up here. And then as that x value increases, that area gets smaller and smaller. The area of the remaining grass gets smaller and smaller as the pool gets larger. So it makes sense here. Now, if you notice, we're also asked to adjust this graph here for the valid values. Okay, so in this case, if we're just dealing with a quadratic -x squared plus 400, then it's going to look like this, right? If there's no word problem attached to it. If you take y equals -x squared plus 400, plug it into Desmos, it's going to give you a graph like this. However, we're dealing with a word problem here, so we actually have to adjust this graph over here. And if you think about it, notice x, it definitely has to be greater than 0. Right? We can't have negative values of x. That wouldn't make sense, a negative dimension of the pool. So in this case, what we can do is we could just erase all of the negative x values. So we would erase all of this over here, like that, right? Any negative x values, they don't make sense in terms of this, word problem. Okay. Another thing I want to mention, if we go back here, so let's go back to this abstract graph for a sec. So we know what the y-intercept is, right? We know what this is. This is 0 and 400, right? We got that from just the basic transformations. However, what are these x-intercepts here going to be? Well, in future sections, we're going to find these x-intercepts with different kinds of methods, with factoring, with quadratic formulas. In this case, we know that these x-intercepts here, what's the y value of any x-intercept going to be? The y value is just going to be 0, right? And then we just have to find these. And so this is a pretty easy quadratic to deal with in terms of just algebraically finding the x-intercepts. We just plug in 0 for y, and then we could just isolate for this x. Isolating for the x in this particular equation is easy. So what we could do, we could bring the negative x squared over, so we'd end up with x squared equals 400. And then what we can do is, to get the x by itself, we could square root both sides to get rid of that squared in front of the x. So we'd end up with x equals, what's the square root of 400? It's 20, but the square root of 400 is plus or minus. The square root of anything is always plus or minus. So we end up with two values here. It's plus or minus 20. And so this x-intercept is negative 20. This is positive 20, like that. Right? So in this particular question, finding those x-intercepts is easy. When you end up having a quadratic like a full one in that ax squared plus bx plus c format, then it gets more complex. Then you got to use different methods or processes to find these x-intercepts. We're going to go over those in future videos, but this one was pretty easy to isolate for the x because there was only one x value. If this was like negative x squared, let's say, I don't know, plus 5x plus 400, then it'd be a lot tougher to isolate for that x, right? But the x was just by itself. There's no bx in this case. So it was easy to get those x values here, right? So if you're looking just at the abstract quadratic, y equals negative x squared plus 400, that's how it's going to look. It's going to have a y-intercept of 400. It's going to have two x-intercepts of negative 20 and 20. If you plug this into Desmos, that's the graph you're going to get. Now, going back to our problem, this part of the graph we erased, right? According to this word problem, we explained why. Now, this here, though, this intercept, it's 20 and 0, right there. Okay, now, we mentioned in this particular case, I just want to go into a little bit of detail. We mentioned what this y-intercept means for this word problem. This y-intercept, this point here, represents no pool, right? If the pool has a side length of 0, then the area of the remaining grass is just going to be the total grass field. There's not going to be any pool there. It's going to just be that 400. Now, what does this intercept represent, this 20 and 0, according to this word problem? Well, this represents if the pool has a side length of 20. If the pool has a side length of 20, then notice it's going to take up the entire field. And so there's not going to be any grass remaining. So that A value is going to be 0 in this case. So this intercept here represents if the pool takes up the entire field. Right? That's what this represents. This intercept, this x-intercept, represents in this word problem, right? So I just really want you to understand what is happening here graphically, but also intuitively according to the word problem. Taking your time to understand this, future word problems are just going to be a lot easier for you to deal with in your mind. Now, what about this portion over here of the quadratic? So we mentioned how this portion we're not going to be looking at because we can't have negative values of x. But what about this portion over here? Well, notice that this portion we're also not going to deal with. We can erase that because we're only dealing with a grass field that has a side length of 20. And so we can't fit a pool that has a greater side length than 20. So like values of 21 or 22, those would be invalid. They would give you a negative area for the grass remaining, which wouldn't make sense in this problem. So the limit that this pool can be, it can only have up to a side length of 20. And so anything after that we don't have to worry about in this problem. Okay, and so this here represents the graph, the proper graph for this, this scenario. Okay, that's what it means by adjusting your x values. So notice that the x values, they could only be between 0 and 20. They could also be 0 and 20 as well. Those extreme cases, if you don't have a pool and if the pool takes up the entire field. So those are the valid values of x. And notice what are the valid values of a? Well, it could only go from 0 to 400, right? It will be 0, a, the area of the remaining graphs would be 0 if the pool takes up the entire field, or it's going to be 400, up to 400 if there is no pool, right? So those are the extreme cases. Those are the valid values of a, right? So the abstract quadratic, it looks like this, but when we take that quadratic and apply it to a word problem, this is the graph that we would be looking at, right? So just be aware of how sometimes you gotta take stuff out of a quadratic or any graph, any abstract graph, to make it make sense with the word problem. Okay, so that ends up being the graph for part B. Now in part C, what they're asking for is how does this equation change and how does this graph change if we change this side length over here? Well, if you notice what's going to change, notice that this pool is not going to change, right? We're still going to have this x here. So let's go back to the beginning. What's going to happen if we change this? Well, let's say that instead of 20, it was 30. So if we put 30 here, notice that this is going to be 900. And so what would change is, okay, right now we got negative x squared plus 400. Well, if we up it to 30, we're going to end up with negative x squared plus 900. So notice that the only thing that changes is that k value. So that's all that's going to change in the equation. Only this number is going to change. And graphically what that means is it's going to change the vertical translation. So that's the explanation. I'm going to show you graphically how these changes look. But that's all that changes. The k value in the equation, right? It's either going to go up if we're dealing with something greater than 20, or it's going to go down. Like if we dealt with a field that's 10, this would end up being 100 instead of 400, right? And the way that's going to affect the graph is it's going to shift the graph up or down. If we're dealing with a higher k value, it's going to shift it up, right? And then if we're dealing with a lower k value, it's going to shift it down. So that's how the equation and the graph is getting affected. It's just shifting up and down, right? Only the k value is being affected. Now graphically, the way that looks is if here, let's draw this out. So this graph here is y equals negative x squared plus 400, right? We have an x-intercept here of 20 and 0, and then over here we have an y-intercept of 0 and 400. Well, if we shift this graph up, right, if you think about it, if we're going to shift it up, what's going to happen is now the vertex is going to be up there, and it's going to be like this. So not only does this shift, that y-intercept shifts up, but the x-intercept is going to be shifted to the right. Right? That's basically what happens. If you think about it, like if we extend this quadratic, remember if we had the abstract quadratic, if you shift it up, it's going to have this shape up here, and so that x-intercept is going to be further out. Okay? If we decrease the size of the field from 20, then what's going to happen is this is going to decrease, and there's going to be a lower vertical translation, so it's actually going to just start. The vertex is going to be up there, and then the x-intercept, it's going to shift to the left, like that. Right? So if this is our graph over here, okay, if we increase the size of the field, it's going to increase the k value, which means it's going to shift the graph up. If we decrease the size of the field, it's going to decrease that k value and it's going to shift the graph down. We're going to end up with a graph like that. All right, and it's going to decrease these valid values over here, right? It's obviously going to decrease the x because we're decreasing that, but it's also going to decrease that valid area amount, right? Because we're going to have a smaller field to work with. Anyway, kind of a lot of explanation there. Probably repeated myself a lot of times, but I just really want you to understand these kinds of word problems, what is happening. So when you run into these, whether in your homework or on your tests, you can just understand them a lot quicker.